right. Thank you. Hello, everyone. My name is Harsha Kokel, and I'm a PhD student at University of Texas at Dallas. And today I'm presenting our system, LARA. It's a human-guided collaborative problem-solving agent. And this is joint work with a bunch of folks from Washington State University, Colorado Boulder, UPenn, and UIUC. The system was developed as part of 5+ years long project with the support from DARPA. And all the authors have contributed in different components of the projects, but in this ACS conference, I'm presenting or demonstrating the system as whole. And I'll be happy to take any questions at the end. And I've joined the Slack channel, so feel free to ping me there as well. So let's get started. Okay, human-machine collaborative problem solving is challenging. It has been a long-standing problem in AI, and there are various reasons why this problem is challenging. Here, we are focusing on following 6 problems. First is a shared perception of the world. Collaborative problem solving requires humans and machines to have a shared perception of the world. Second, it requires contextual understanding. It also requires machines and humans to be context aware and capable of understanding that some action or instruction might make sense in a particular context, but it might not make sense otherwise. Third is sophisticated language understanding. As natural mode of communication for humans is natural language. To be user-friendly, it is essential that machines are capable of understanding sophisticated natural language. Fourth is bidirectional communication. We obviously do not expect machines to understand everything humans say. So when they do not understand something, they must be able to raise their hands and ask questions. So collaborative problem solving needs bidirectional communication. Fifth is composable vocabulary. So this is one of the core challenge which I feel is deserves more attention. When humans collaborate with other humans to solve a problem, with experience, they develop some form of gestures, or they might develop some mode of operations, which makes it easier for them to collaborate again on the next task. Similarly, when humans are collaborating with machines, we want machines to learn from the experience and maybe have a composable vocabulary so that a new concept or new task can be taught as a composition of existing or earlier tasks. And maybe next time around when we have to we have to do the same task again, we don't have to tell machine all the paths. We can just tell, okay, get me a coffee instead of telling the route to Starbucks or something, right? And finally, we expect the machines to do their part glitch-free. So once the communication and the understanding part is taken care, we also want the machines to be able to do their part of problem solving in a glitch-free manner. To address this combination of challenges, we developed a collaborative problem solving task, which was inspired by Block's World. As you might know, Block's World domain has been used in AI for a long time, at least as early as 1970s. For instance, Patrick Winston used Block's World for learning structure description from examples. And even today, automated planning community and neurosymbolic methods that are coming up use Block's World as one of the domains for their evaluation. So we developed a Block's World style building task in a Minecraft domain. Here we have the Minecraft simulator. In the Minecraft environment, we have a white stipulated area, which we call build region. And the task is to build different block structures, different structures from blocks in the Minecraft domain. And in this environment, we have a builder, which is the Minecraft avatar here. The Minecraft avatar can place blocks in the build region. But unlike the actual Minecraft game, where a human user can directly control the avatar, here, humans cannot control the avatar. Instead, we have a chat interface, and humans who can actually see the target structure play the role of an architect. And as an architect, humans have to instruct the builder via this chat interface. So the target structure is constructed in the build region. So I'll just show a small demo here to get everyone at the same page. Okay. So this is the target structure which architect is seeing. And let me play the video. Okay, and this is the build region, and here is the builder. There's a message from the builder which says, "Hello, architect, I'm ready." And I'm not sure if you guys can see it, but there's a small chat chat interface at the bottom where the architect can type, and the architect is typing the following instruction right now. First, build a red tower of height 4, then add a red row of size 2 on the right of it. So this is the message sent by architect. And then now the builder is figuring out how to make that structure. And then it is placing the blocks in the environment. So that is the task. In this task, we can see that the Minecraft builder and the architect, that is human and the machine, both need a shared perception of the build region. The builder needs to understand the context here. For example, when the architect said that add row to the right of it, the agent or the builder has to understand what it means in that context. The agent needs to understand natural language because the interface is a chat interface. And builder also needs bidirectional communication because sometimes builder might need to elicit additional information from the architect. For example, if an architect forgets to mention the height of the tower, then the builder should be able to query the height. And if say the architect asks the builder to say build a fort, but the builder doesn't understand what a fort means, the builder should be able to communicate back to the architect and try to indicate the architect that I don't understand this. What does it mean? Let's decompose it and use these structures which I understand to build a fort. So something like that. So we want a bidirectional communication here. And more importantly, we want a builder to be able to learn new structure from the small structures. For example, here, when where we saw that the architect architect instructed the builder to build a L structure using a tower and a row. But now we would want the builder to understand that this is a L structure, and later on, the builder should be able to build L structure directly without mentioning the tower and the rows. And finally, we want the execution to be glitch free. So what I'm trying to do here is essentially trying to convince you guys that the building task in Minecraft domain is a challenging human machine collaboration problem. And now I'll describe the system that we built to address these key challenges. Our system actually builds on advancement in several related areas: natural language processing, ILP, automated planning, and statistical relational AI. I will not go into the details of each and everything, but I'll be presenting the whole system. Okay, so first, here is our problem setup. We assume some minimal essential pieces of prior knowledge that are known to both the players, the architect and the builder. These pieces include some colors. What are the different colors of blocks that are available in the environment? We expect both the players to know that. Then we know we have encoded the knowledge about directions into the builder. So builder understands what the top, bottom, east, west, or right, left, and front and back is. Then we have encoded 8 primitive shapes. 5 of them are shown here: tower, row, column, cube, cuboid. The remaining are the block and square and rectangle. And we have something called block indicators. So block indicators essentially are pointers to a single block in a structure, which are known to both, which are basically provided as additional knowledge to both the builder and the architect. And here is our overall system, which contains 4 main modules: a Minecraft simulator, NLP parser, planner, and concept learner. In the Minecraft simulator, we have 2 main tasks. First is the dialogue manager that handles all the messages of the chat interface. And second is an agent control system. Agent control system is the system that would actually send the build plan to the Minecraft simulator or Minecraft API. So we use a Malmo API by Johnson et al. 2016 that essentially provides us a interface to communicate to the Minecraft environment where we want the builder to place a block and things like that. And then we developed a dialogue manager, which triages the messages from architect into 4 different categories. That is build instruction, clarification, concept explanation, and operation commands like undo or forget a particular shape, which the builder has recently learned or something like that. And the messages from the builder are essentially generated by the dialogue manager. And for that, dialogue manager maintains slots for like slots that are templates, and it fills in the slots based on the error code or the message that the builder sends. Then we have an NLP engine. The main task of the NLP engine is to parse natural language instruction to a logical representation. We use first order logic representation here. So for example, the statement build a tower of 4 red blocks is converted to a logical representation like this. And for parsing the natural language to logic, we use 2 different parsers. One is a template-based parser, which is essentially using again the slots and like template statements, and which fills the slot. For example, build a dash of dash blocks could be a template, and because the first space is in the first slot we see tower, we assign a tower as a predicate here. So that is the template-based parser. A template-based parser are fast, but they are very limited. So essentially, as the project progressed, as the project progressed, we moved to a AMR-based parser. AMR-based parser are so AMR is the abstract meaning representation, which looks something like this. Natural language sentences are converted to AMR representation by an AMR parser, and we can convert AMR parses or AMR representation to logic representation. This was shown by Bose 2016 paper. So we use their mechanism. As part of our project, we collected data sets in this building task. We had human users playing the architect as well as the builder, and we generated the chat data set. And we learned AMR-based parser for the Minecraft Minecraft domain. The important thing, or the differentiating, or the essential challenge that we were facing was about the spatial representation. As you saw, we had to explain that, at the row on the right or the left of the tower, these spatial representations which were not well handled by AMR. So we had to train that. So that more detail about that AMR parser is presented in Bonn et al. 2020 paper. And finally, No, sorry, not finally. This is the third module, planner, which converts logic representation to goal. Then the goal is sent to the hierarchical planner, and then the plan goal is converted. The planner would provide us a sequence or sequence of action or the plan, and this plan is then sent back to the agent control. This plan is sent to the agent control, which essentially triggers the Malmo API and executes the plan. Some important thing here is the that besides just converting besides translating the logic representation to goal representation, here we also have a repository which provides the additional knowledge about different shapes. So for example, tower cannot have a width. So these are the things that are provided by the knowledge from the repository. And a tower requires a height. So if the height is missing in the logical sentence, then these such information are then queried to the architect by the builder. In the final module is the concept learner. This one is I think is the most critical part of the whole system, where we have used or we developed guided one-shot concept induction framework, which is presented in Das et al. 2020. Here, let me demonstrate the concept learning part and then talk about what it does.
2 minutes left.
All right. Okay. So here, once the structure is complete, the builder is asking if you want to save the structure for future use, and the architect is saying yes. Architect provides a name for the structure, which is L, and the builder asks what are the dimensions of the L, and the architect is mentioning that L has height of 4 and width of 3. Now, to learn that this is a L structure, the builder is essentially asking a few yes/no questions to the architect. The first question the builder asked is, should the height of the new structure be same as the height of the tower? Notice that we built a tower of height 4, and now we are saying that the L has height of 4. So the concept learner is looking at the space of concepts. I'm sorry. So it's actually asking few yes/no questions to the architect to narrow down the search space. And notice that the concept learner has to learn the new concept only from a single example. So the search space is quite big. A few yes/no questions can help guide the concept learner. In the concept learner, we use normalized compression distance to measure the difference between the different structures. So here, after 3 yes/no questions, the structure is learned successfully, and then in the next episode, the architect can directly ask the builder to build a red L of size 3 by 3. So you see that the builder is able to learn the structure from a single example. So overall, this is the framework where we have the Minecraft simulator, which receives the chat from the chat interface, and the dialog manager then triages if the statement is, if the current sentence is an instruction. If it's an instruction, it sends it to NLP parser. If it's a clarification, it sends it to planner. And if it's a concept explanation, it would send it to the concept learner. So dialog manager here triages that, and then the relevant module is triggered, and the planner NLP parser would provide a logical representation to planner, and planner would provide the block placement goals. The concept that is learned in the concept learner is then saved in the repository for further use. So overall, we wanted to show that our system can achieve bidirectional contentful communication. That is the communication from the builder is contentful. It can ask for missing dimensions, ask for reference points, etc. Like which on what on right of which block, etc. It can ask those questions. The builder is context aware. We learn a composable we have a composable vocabulary, that is a new structure is learned as part of or a combination of the previously known structures. And once a new structure or a L is built, we can then combine L with a tower to form a use. So it is composable. The system has a limited robustness. It can proceed without restart by, say, doing an undo, and it does not lose context. If you want the system to forget some particular shape, then we can also trigger forget operators. And the system is habitable. That is, if the correct questions are, or if the sentence provided by the architect is not understood by the builder would guide the architect on what kind of questions should be asked. More videos or for the more demonstrations of the project are available on the project website, and the link is in the paper. Sorry for the cough. Are there any questions?
Let's thank our speaker. Let's take one, if you don't mind, let's do one question from the Slack. Dustin Dannenhauer says, I'm curious how far you were able to go with a human adding new structures. You show the rectangle as the most complicated shape. Could you keep going and get to the point of guiding the agent to learn about walls, ceilings, etc., to being able to build a house, for example?
We were able to build a house. The limitation here is that current concept learner only composes 2 existing shapes at a time. It is not learning, like 3 structures at a time, or compose 3 structures to learn a new shape. So that is the limitation. But we were able to build a very minimalistic house, like 2 slant lines and then 2 towers.
Okay, great. Let's thank our speaker again. Thank you, Harsha.